So today's lesson, we're also going to be doing projectile motion, but whereas yesterday we always launched things horizontally, today we're going to launch them at an angle. It's really the only difference we're going to talk about. So when we launched them horizontally, the big thing was that, let me just draw this. If we launch something horizontally, right, the big thing was that your initial velocity in y was 0 because it had no y component. But now that we're going to launch things, for example, like this, it's going to have a portion that is, or a component that is in x and a component that is in y. So our initial velocity will have both a horizontal and a vertical component. So it's going to be the same steps as yesterday. We're going to split everything into x and y components and solve our equations on both sides. But before we do that, we have one additional step involved. We need to figure out this triangle, which will be a right angle triangle, but we're going to need to solve for those x and those y components. Once we have those x and y components, we can put them separately into our given information table here into x and y. So let's look at the example and we'll work through it. The example says a paintball directed at a target is shot at an angle of 25 degrees. So just estimating this, but there we go. So this is going to be our initial velocity. If paint splats on its intended target at the same height from which it was launched, so let's imagine that that's the ground and there's going to be a target right here on the ground. There's our target. So it's going to go all the way over and hit the target like that. 3 seconds later, so we know what time is. Time equals 3 seconds. Find the distance from the shooter to the target. So this entire distance here is our horizontal distance. So delta dx, which if you remember, we also called that range. So that's what we want to find out. We want to find out the range. So let's make our little chart. And I'm going to write what we know in x and what we know in y. So there's only 3 things you can look for in x. Initial velocity in x, displacement in x, and time. Right now we do know what time is. It's 3 seconds. I don't know what this is. In fact, this is what I'm trying to find. And initial velocity, I don't know yet either. What about in y? Well, one thing we always know about y is the acceleration in y, which is 9.81 meters per second squared down. I don't know initial velocity in y. I don't know final velocity in y. I do know time, right? Remember, time's the one thing that goes across both components, so that's 3 seconds. And I also know my displacement in y. So let's think about this for a second. I don't know how far it's moved, but I know my displacement in y, and that's written right here. It says it hits its target from the same height as which it was launched. So yes, the ball is going to move from here all the way over to here. And therefore, its position in x has changed a great deal. But if it hits the target at the same height from which it's launched, then its y position hasn't changed at all. So we know that the displacement in y is actually going to be 0. Okay, you have to remember displacement is a vector. It's not distance. Right? Direction is important. Okay, even though this says it's launched from the same height, again, displacement is not height either. because height is a scalar quantity. Okay, it would be very different if it landed on top of a building. Then your displacement would be some positive up value, or if you threw something off of a cliff, then its displacement would be some negative value because it's down. Okay, but it's always comparing your position, your change in position. That's what displacement is. I should be writing vector signs on all of these, except for time, of course. All right. Now, one thing we can do is we can split this initial velocity vector into its horizontal and vertical components. And it tells us this angle is 25 degrees. Now, because I don't know any of the sides, I can't necessarily solve for these two sides because I don't even know what this hypotenuse is. But I can at least write an expression for each side. So for example, our vertical component, I can use the trig ratio, the sine trig ratio, because the sine of 25 equals opposite over hypotenuse. Right? So sine of 25 equals opposite, which is VIY, over hypotenuse, which is VI. So multiplying both sides of that equation by VI, I can say that the vertical component is equal to that hypotenuse times the sine of 25. And even though I don't know what that hypotenuse is, I can still write an expression for that. This is why I've told you before, it's good to get into the habit of writing variables instead of numbers all the time, because sometimes expressions can help you, even if you can't solve for the actual number. Okay? And we can do the same thing to solve for our x component. It's just equal to our hypotenuse or our initial velocity times the cos of 25 degrees. All right, so if I want to figure out what this displacement is, I need to know what this component is. And this is sort of almost like a domino effect. If I want to know what this component is, I need to know what initial velocity is. Well, if I want to find initial velocity, it would help if I knew what that vertical component is. So it's really like a domino effect there. So what I can do is I could look for VIY using my equations of motion in our y component. So in this case, I want to find VIY, and this is the three pieces of information I know. The one I don't care about is our final velocity. So let's use the equation that does not have final velocity in it, which would be our displacement equals initial velocity times time plus 1/2 acceleration times time squared. And we know that this displacement is going to be 0 because that's our vertical displacement. Okay, since that term is 0, I can divide every term by time, and I can only do that because I know time is not 0. If a variable could be 0, you don't want to divide by that because then you're dividing by 0. But I know it's going to take more than an instantaneous amount of time to actually travel that distance, so I can divide every term by time. 0 divided by time is just 0. That gives me 0 equals to VIY, and a square will cancel there, plus 1/2 a delta t. So now I can just rearrange to solve for VIY. VIY equals, bring this term to the other side, make it negative 1/2 a delta t. Now that we have our expression, we can substitute what we know. Now acceleration is 9.8 meters per second squared, but it's down. And we're always using, for now, our coordinate system where up is positive. And we can also make right positive. So that means I need to make this negative 9.8 meters per second squared times by time, which we know is 3 seconds. And that gives us an initial velocity in y to be 14.7. Okay, so I know initial velocity in y is now 14.7 meters per second. And now I'm just going to go through that domino effect. So now that I know what this is, I can solve for VI. So I'll change color because it's going to get a bit crowded. So if I divide both sides by the sine of 25, I can get VI equals 14.7 divided by the sine of 25, which equals 34.8. And now that I know what initial velocity is, continuing the domino effect, I can figure out what the initial velocity in x is. Change color again. So this is going to be 34.8 times the cos of 25. I'll just write it here because it's the same color. Which is 31.6. And now that I know what initial velocity in x is, our last domino effect is to find that the displacement or the range in x is equal to the velocity in x. And I write initial velocity in x, but because your velocity in x doesn't change, you can just write vx. Because there's no acceleration in x. Gravity doesn't act sideways, it only acts up and down. In reality, there is air resistance, but air resistance makes this problem way more complicated. That would be like a university kind of physics question. So we're going to ignore resistance. So we're on Earth, but there's no air. And we're just going to ignore how bad that would be. Right? And then we're going to times that by time. So that's our equation when acceleration is 0. And we get initial in x, which is 31.6 meters per second, times time, which is 3 seconds. And that gives us a range of 94.7. And that is a vector. If you want, you can just label this to be forward, whereas this one is up. So our vector is just 94.7 meters forward. All right, so looking at the thinking problem, we need to figure out what angle we would fire something at or throw something at to get maximum range. So we're trying to find an angle that's going to balance or maximize time of flight with horizontal velocity to get maximum range. So let's say we throw it at an angle, and let's just call this angle theta. We don't know what it is. That's what we're trying to figure out. And we're going to throw it with some initial velocity, vi. Now we can solve for the components. This will be Vx will be Vi cos theta. And our initial velocity in y will be Vi sine theta. So if we look at our x component, so I'm going to look at x component. It's only one equation we have in x, and that's this one. Our range is going to equal our velocity in x times time. And if we look at our y, Well, we want the equation that doesn't have final velocity because that's not the one we're interested in. We have displacement in y is our initial velocity in y times time plus 1/2 a times time squared. Now, this problem is going to be like the previous problem we did. We're going to do this sort of maximum range competition on flat ground, so on a field. So that means that our displacement in y, or our change in our y position, is going to be 0. So that's one of the conditions that we're going to have in this little competition. Now what I can do in each equation is I can substitute these expressions up here that I have for our x and y components of initial velocity. And this will give me that the displacement in x is vi cos theta times time. And over here I have 0 equal to vi sine theta. So I'm just replacing viy with vi sine theta times time plus 1/2 a times time squared. All right, so what do we have here? We have two equations that I want to work with. And so what I'm going to do is I am going to rearrange this one to solve for time. So I'm just going to write it as divide both sides by vi cos theta, and you'll get delta dx over vi cos theta. And then I'm going to substitute this value in for the times in this equation. So yeah, serious algebra going on here. This is going to give us vi sine theta times by this. Just move over. Oh, I can't move over. I'm going to run out of room. Plus 1/2 a times this. All right. Now, actually, I could have done this earlier. That would have been simpler if I had divided everything by time. But I'll just do it here. Right? It would have been simpler if I did it here. But I'll do it here anyways. So now this leaves us with, I'm going to bring this whole term to the other side. So I'm going to have minus 1/2 a times delta dx over, I'm going to scroll down, vi cos theta equals vi sine theta. And then I'm going to multiply, so in the denominator here I have a 2, a vi, and a cos theta. So I'm going to multiply both sides of the equation by that. So I get minus a times our range equals 2 times vi squared times sine theta times cos theta. Okay, and then divide both sides by negative a, so you get delta dx equals, and I can actually say that a is going to be 9.81, and it's going to be negative 9.81. So let's call it negative g, where g is just 9.81. I'm just doing that because I want to get rid of the negatives. So this will leave me with vi squared over g times by, and I'm purposely moving the 2 next to the sine and cosine, because I don't know if you've seen this in math before, but this is a trig identity, where 2 sine theta cos theta is the identity for the sine of 2 theta. So this is a range equation. Again, this range equation is specific to the fact that we canceled, or we set the displacement y equal to 0, so it's on level ground. So it's saying that our range in x is equal to vi squared over g. So we can't change that, right? Because we can't change vi unless we go to the gym and increase our muscle mass, and we can't change g unless we go to the moon or something. All we can do is change theta. Now, the sign of something goes between 0 and 1. So if we want to maximize range, then we need to make sure that the sine of 2 theta is going to be equal to 1. Since the sine of theta oscillates between 0 and 1, we want it to be the biggest number possible. That's 1. So taking the inverse sine of that, you get 2 theta. The inverse sine of 1 is just 90 degrees. And if 2 times theta equals 90 degrees, our answer is solved. Theta must be 45 degrees for maximum range.